Okay. Welcome to lecture 20. The topic of our discussion today will be locally recoverable codes. So the definition will be very similar to our earlier topic from last lecture, locally decodable code. But unlike locally decodable code, so if we do not have efficient implementations, we'll actually have very efficient implementations, and these are actually used in practice. So I think Microsoft Azure, their messaging service, uses the LRCs, which I'm going to be talking about. A very cute application of Reed Solomon codes. So today will be a short lecture. Okay, so let's sort of motivate. Yeah. So your data is on, you have a Gmail data which is held on the Google Cloud. So it's your Gmail data. So think of you as just one. Let's forget that there are several Gmail users. Just you are a user and it's on the Gmail cloud. So it's spread. It's on several data. Your data exists on several data servers across the world. This is how it's being stored. And certainly every now and then a data server goes up, goes down. You want to still, despite that, no matter when you access Gmail, you want to be able to, your email should be fetched. Just fact that you're one. So in particular, Google can't be putting all your data on a single data server somewhere, because there could be occasionally the data server could just, so let's assume there are no corruptions. It's just every now and then data servers do sort of go down for whatever reason, or the response time is much slower. It goes down. They can't put all your data on this one. They can't even split your data and then take each data and encode it locally on a data server. It has to, there has to be some sort of, your data has to be spread across several data servers. And even if a few data servers go down, you must still be able to answer responses. This is the question. This is a natural question that you want to solve. So you want to know how to write your data across this one. Standard way Google does it, it just repeats, it just use the majority encoder. It just has the same data copied elsewhere, so that if one of them goes down, you can access it from the other. This is one way of doing it. And as we all know, the majority code has a very, this is the repetition code that's being used. This is not it's not a great code. It's not a great code to question which we ask is, are they better codes? And certainly we saw the code from last time, the locally decodable code, precisely solve this problem. They say that if 1/10 or say 1/100 of the locations also go down, we will be able to recover with a very few queries. This is what LDCs were meant for. So if you had a good LDC, you can certainly solve this problem. But unfortunately, as we saw last time, we don't have good LDCs. We have LDCs in which the locality is polylog-n. This was using Reed-Muller codes. And any LDC using, we had a LDC with locality 2, but the rate was exponential. And then we gave examples. The whole of last lecture was to construct a sophisticated LDC using matching vector codes. The great thing was it got 3 query or more, but with sub-exponential. Google is not going to repeat your message as a super polynomial number of times. In fact, they would want encodings in which the rate is constant, not even constant, the rate is close to 1. They want the redundancy to be as little as possible. So you don't, redundancy costs them extra data servers and all of this. So you want that to be as little as possible. So what we want to ask is, as we actually asked, is the LDC definition way too strong? Are we expecting way too much? Is that the real problem that these guys face? We want to access the failures of occasional data servers going down. Are they handling a much stronger problem? Is that why LDCs are much harder to construct? Is there a simpler problem question which we can handle? And the thing to notice is, what were LDCs trying to handle? The LDCs were trying to handle the case that even say a constant fraction, like 1/10 of the servers, data servers go down, you are able to recover the message. Every message bit you're able to recover, every code word. If it was a locally correctable code, every code word bit. But this is never the scenario. Like 1/10 of Google's data servers are not going to go down, or 1/100th of it. the data servers are not going to go down. It's going to be every now and then, it's going to be constant number of them going down, not a constant fraction of them going down. And once you go down, they will locally repair it down. So what you want to be able to recover, what you want to address is a much weaker problem. You want to say, if every now, the most common notion of failure, which happens like almost on an everyday basis, is a constant number of the data servers going down due to various problems at their end. These you must be able to handle extremely efficiently. If a constant fraction goes down, which happens possibly say once a month or once a year or so, at that time you're willing to do a global decoding. You're willing to read the whole thing and spend time, because that's a rare occurrence. Whereas LDCs were designed to handle a constant fraction of errors. And so this is the problem that we have at hand. You don't have a constant fraction of errors. You only have a constant, the most common error scenario is a constant number of errors. Some reason this link is not working, this data server is not responding. You want to be able to get it from another data server. So what we want to come up with are codes which most of the time, as long as they're just one or two corruptions, you are able to recover with very low locality. If there's a constant fraction of locality, then the distance of the code takes care of. That is, there's a good decoder, you will do globally, you will decode the thing. Whenever there's a massive failure, a catastrophic failure, you will use global decoding. At that point in time, so we are weakening our requirements of what we want from the code. So, and that is what I'm going to call as locally recoverable. So it's codes which are basically, it's going to be the requirement is weaker than LDCs. So LDC can locally decode if there's a constant fraction of errors. That's what LDCs are. LRC is going to be can locally decode if there's a constant number of errors. But yet you also want to recover if there's a constant fraction. So you'll both put 1 as well as 2. You'll say if there's a constant fraction of errors, you globally do. And so 1 is typical failure. And 2 is what we call catastrophic failure. So in that case, it's okay to spend more time and read the whole sort of. Is the motivation clear? Why 1? So they're going to weaken what are requirements of 1. So in this case, it's constant number of errors. In this case, it's globally decoded. That's going to be the difference between this one. You can also incorporate more things about. So the topic after LRCs were introduced about 15 years ago, 2008 or so. And then there have been a lot of work that goes on. There's something called maximum recoverable codes and all, which basically now try to understand the topology of the way because now how servers are maintained. It is the data servers are spread across the world, but some of them are local, some of them, so there are 10 data servers in one data center, another 10 data servers in another data center, so many of them. So if you want to, even this locality, as long as it's within a data center, it should be cheaper. Across data center, should be more expensive. So you can come up with the various notions of your, so depending on the issue. We will work with this very simple one, that is, if a constant number of the servers fail, you should be able to recover. And if there's a constant fraction, you should be able to recover actually with very local access. Just reading a few other data servers, you must be able to recover what's there in this missing data server. If a constant fraction fails, then you spend time, go and do a global decode. We'll actually, for today's case study, we'll make it even simpler. We'll just that constant number, we'll make it 1. Suppose one guy fails, I want to be able to recover. So, two is guaranteed if the underlying code that you use has good distance and a good decoding algorithm. So 2 is always guaranteed with that. So what we want is also a code which not only has good distance and good decoding algorithm, which will guarantee 2, but also from the fact that it can get around 1. That is, every now and then when one corruption happens, it's able to sort of work around. So that's the one. Let's actually define the object first, and then we will. So once we define the object, we will see if there are possible constructions for it. Notice, and we want the rate of this code to be very, very good. We want the rate of the code to be constant, first, certainly constant. There's no, these are actually code we are going to use in practice. So we want the redundancy should be constant. In fact, even better, the rate should be close to 1. The amount of extra redundancy bits you're adding should be very, very small compared to the actual bits. You don't, these clouds are not going to use rates which are like 100, they're not going to do 100 repetitions. Yeah. So well, let's see if we can get all of them. So let's start off with if we can do this. So let's see a definition. So I'm going to define what I'll call. So for today, we'll talk about local recovery. So from one corruption. That's our whole lecture is going to be based on this. So you define it now. So what's the goal going to be? What's the plan for the lecture? It's going to be a fairly short lecture today. We're going to define this object. We will see a clean construction using the Solomon codes. We will ask, this is the best that one can do. We will also do a matching bound, and we'll see some further modifications of this construction. That's what. One period. So we'll define an object for it. So there will be 2 parameters of interest for us. One is R is the locality parameter. That is, if this data center fails, this data server fails, how many other data servers you have to access in order to recover the message from this. And D is the distance of the code. These will be the 2 parameters we want. We will of course ask what is the rate of the score, what is the block length. I give you all of this points. One. So we'll see that speed. In general, we're talking about, and also there will be an underlying alphabet. And alphabet, because of this particular instance we're talking, we will not be focused on small alphabet. These are what is stored in a single data server. So you can think of that as a large alphabet. That's this is not the binary alphabet which we're talking about. It's a large alphabet. This is the one. So we'll say we're going to have an NKT cube code, and all these definitions work even for non-linear, but I'll just make it will restrict to linear codes. In fact, all the constructions you will see will be linear code. There will actually be modifications of the read Solomon code. NKT cube code is RD message symbol recoverable. Or just short, right, RD LRC. if the following code. So you think of C as going from 01K to 01 and one, certainly the first thing which we want is D is just the distance to that D is the same as the distance to the port. The only property I need to say is what is R. But the way we define and what is give the definition, it's going to be fully combinatorial. There's not going to be any algorithmic requirement. I don't want any efficiency requirements in this one. All the implementation we'll see will be efficient. So the main thing which we have to say over here is recover our local recovery. That is for every I in K. So for every message symbol, So I'm just assuming this message. So for simplicity, we can assume that because it's a linear code, let's also assume that the code is systematic. So let's assume C is systematic. So the first K symbols of the message are actually of the code word are actually the message symbols. So that is first K symbols of code word is message. Mistake. This is not large. So it's not 01, whatever it is. What do we want from this? And for every I in K, what do we want to say? There exists a set Ri. These are the other locations you would access in order to recover Ri. Particular, these should be certainly a fraction of n, and it should not contain I, such that should you have? I'm going to write it in short, such that C. I'm going to write. Okay, so the Ri implies I. What do I mean on it? If I see the location, if I see what is written in Ri and there are no corruptions in it, from that I can recover the I location. How you do it, I don't care. Notice if you can do it, if the underlying code were linear, then if you can do this actually has to be a linear combination of these guys. For linear code, if you can do it, it has to be a linear combination. Can't do anything. For non-linear code, there will be some complicated function. I don't care, but this is the definition of the script. I want to say that. What do I mean by this? I mean to say that now for every code word, if I just look at the code word values at Ri, using that, I must be able to infer what is the code word value at the ith location. Makes sense? So that's going to be our definition of I in K. I just want to recover the message. Yeah, so there are going to be two definitions for us. We are going to this is what is called an MLRC and an RD-MLRC, and RD-LRC will be the same definition. So you say that C is RD locally recoverable. Just RD LRC. If this condition the condition code with the only restriction that this is ends. Every, let's see. So there will be two different things. This is good. Some remarks here from definition that is RD LRC is certainly an RD MLRC. And the above definition, we don't make any no computation at the problem. It's a combinatorial. It's a combinatorial.
So the first remark falls from that we suppose C is systematic.
Yes, yes,
It's not systematic, it will not be so clear.
it will not be so clear. There you will sort of so then it's not going to be RI server. There is it's not so clear. It's not so clear. So yeah, not so clear. So, but our construction will be this. Construction, we will show, we will give constructions which are RD LRC. Our lower bounds will be for, so even the weaker restriction will give lower bounds. Our constructions will be this one, but they will match the lower bounds that you get. So they will be the best of the pulse that you get. Suppose we take them read Solomon code. So the goal of this eventually is going to come up with codes which have good rate as good as possible. So I don't care about the alphabet, so you can assume the only limitations on rate is a singleton bound for the MDS code. So let's take a MDS code. Can this be an MD LRC, an RD MLRC, or an RD LRC?
Take what?
So take the read Solomon code. So now, right now we want to come up construct LRCs which have extremely good rate. So, and because the alphabet is not a limitation for us, the only limitation on rate that we have right now is the singleton bound. There are no other bounds. So in particular, let's take one of the codes that meet the singleton bound, say the read Solomon code or any other MDS code. And let's ask, is that already an RD LRC?
If one bit is deleted, I can look at any D other bits and maybe even put it.
Can you look at the other bits? You need, if the message was K, suppose it's K, you have to look at K minus 1. So K minus 1, that's not B. No, D, let's keep D to be this one. So it's not the, you can't record from, so you can never have locality which is small r. I'm going to think of r as a constant over here. R ideally is 2, 5, 10 something. So what Richard was saying is an MDS code like read Solomon. Even if one symbol is out, in order to get that, you have to at least look at the degree minus 1, which is in this case K minus 1 locations in the one. In fact, all I want here is there exists one RI. The MDS code says any K minus 1 will be sufficient to record. It has a much stronger property. It is stronger in the sense any K minus 1 works, but the K is very large. It's not local. R is not a small number here at all. R is huge. R is basically as large as the message. This is not something we want. I want it with one failure. I want to be able to look at 5 other things and recover from it. So what we do is we do sort of. So we want to get rates which are close to MDS, what MDS guarantees. So we take an MDS code and modify it. So right now we saw that an MDS code does not have this feature because R will be large for an MDS. I want R to be small for an MDS code. So let's take an MDS code and see how we can massage it in order to get this construction. So let's take In particular, let's take the Reed-Solomon code itself. So let's take a Reed-Solomon code, which is Solomon code or any MDS code. Which is say N naught K D Q code. Where what will be where N naught equals K plus D on my K plus D minus 1. That's the Reed-Solomon circuit. Yeah, where N naught is K plus D minus 1. Let's take this. What we will do is we will add some more redundancy bits. We will modify this code a little bit. We'll increase N naught a little bit so that the distance doesn't change, but it will have now it will have the R local recoverability. So R is some number I'm going to give you. R is some the locality parameter. So let's try to stare at the generator matrix for this code. Generator matrix. Because it's a systematic code, so it's a G is so this is G. The G is sigma. What is it? It's an N cross K matrix. So it maps to X is going to get mapped to the symbol G of X. X is in sigma to the K is getting mapped to sigma to the N. So because it's systematic, what can you say? The first, this is I. The first K by K thing of it is I. So it has I sitting on top of it. Therefore, the first K bits of the code word are exactly the message bits. And then you have say P1. You take this linear combination of the message bits. Then you have P2. Another linear combination of the message bits. That's the next one. How many more of them? You have Pn. This will exactly be how many more? It will exactly be D minus 1. Why? Because N naught is K plus D minus 1. So those are the ones. So each of the PIs, so the generator matrix has this form, if C is systematic. And each of the PIs is in sigma to the Q. Fair enough? We know that this is not our local record. Now, I want to make one observation. Take any RI. What is the support of, any PI? Any PI, I in 1 less than or equal to I less than or equal to D minus 1. What's the support? So it's basically what is PI saying? PI is stating the word out. PI is stating that the K plus ith code word bit is this particular linear combination of the message bits. And that linear combination is specified by the vector PI. Now, so PI has some support. It takes some coordinates, it's adding them, it's going to add them with some coefficient. And my question is, does it involve all the message symbols, or is it just a linear combination of a smaller set of messages? I want to ask, what is this? You follow my question? So each PI represents a linear combination of the K message symbols. What I want to ask is, what's the number of linear combinations we can? So suppose drops a message symbol. Suppose it doesn't involve a message symbol. What do we know about this? An MDS code. Any K code word locations, from that you must be able to recover the message completely. Suppose it drops one particular message symbol. Let's take the other K-1 message symbol locations in the code word corresponding to not this one and this particular thing. This is K code word symbols. From this, can you recover the missing K symbol? Once again, so suppose one of the PIs does not include the K message. So it doesn't. It's not a linear combination. The corresponding coefficient is 0. Then what will happen? Then look at, so suppose P1 will have that property. P1, it puts 0 in the Kth location. Now look at the first K-1 locations in the code word and the location corresponding to P1, now which is the K plus first. So these are K things. From this, you must be able to recover all the K symbols. That's what my MDS tells you. But can you recover?
You cannot say whether it is X or X or K.
Huh?
You cannot distinguish between a codeword C and C XOR with a K.
Yeah, basically you don't have, because this what is written in P1 is just a combination of the first K-1. It's fully determined by the first K-1. It has nothing to do with the Kth guy. Therefore, you didn't need that location at all. But if you didn't, you have only the first K-1. How will you recover the K? Across the K symbol, there's full linear independence. You can't recover it. So this will tell you that in an MDS code, the support of every, when you write it in this above form, every thing should have full support. If it has anything less than full support, you are doomed. So suppose P1. So let's just take P1. So yeah, let's look at the example from the board. Think of K as 4. So this is, we have I4 sitting here. 1 0 0 0 0 1 0 0 0 0 0 1, and then you have some more things. And now suppose this was just 3 4 5. It didn't involve the code. Now in the code word, so this is getting multiplied by x1, x2, x3, x4. And this is going to C1, C2, all the way to say from Cn. Because it's MDS, any 4 symbols out here should be able to recover this one. So now let's look at just symbol 1, symbol 2, symbol 3, and the one corresponding to this. You just can't recover the K symbol from this. Because firstly, this is redundant. Because this is, if I have these 3, I already have this. So this one is just not recoverable. So in particular, this has to involve every. So, and this is true for each one of them has this feature. This is at least a necessary condition, not a sufficient condition. Or you should have this feature for it to be MDS. So the support, when you write the MDS matrix in this form, the support of proof of this is just otherwise, suppose J Norton support PI, then K minus J and K plus 1, sorry, K plus I, K plus I locations do not determine the message. So now let's take this. What I will do is I will chunk up. So let's take the last guy. Let's take PD minus 1. So that's some vector of this one. Let's break it up into this. This is coupland R. This is of length R. Let's break it up into as many things. This will be of length less than or equal to. So let's break it up into L, which is K. That's the number of parts. So I'm writing the last guy alone this way. So what am I doing? So let's call PD minus 1 as, so let's call these sets as S1, S2, all the way up to SL. The size of each SI is equal to R if I is less than L, and it is less than or equal to R if I equal. That's how I have set it up. And PD minus I, I'm going to write it as Q of 1 plus Q of 2 plus Q of L, where support of Q of I is exactly S. All I'm doing it is taking the long CI and just calling this, zeroing out everything outside SI, calling that QI. Is that is the definition of QI? It's almost obvious. It should be clear. There's a lot of words, but that's QI. Now let's look at, consider the following generative methods. We have IK as before. We have P1, P2, all the way, let's go all the way up to PD minus 2. Now I could have put P1, PD minus 1, that guy, but instead of that, I'm going to put these guys. I'm going to put Q1, Q2, and so on, all the way up to Q3. So firstly, notice what is that's, so this is the new generator matrix G prime. G prime is a sigma K cross N, where what is this N? This N is, it's K plus D minus 2 plus L. And that's exactly K plus D minus 2 plus, what was it? It was but I want to claim this is actually R locally recoverable. Why? At least mess. So I want to know that I want to make the claim. Claim that the code given C prime, which is G prime plus X and sigma K, is R D MLRs. Firstly, let's look simply. Is it what's its distance? Is it this? So the original code had distance D. Does this code have still distance D?
Each QI support at most AYR.
Yeah. So let's take a non-zero code word here. I want to say if you continue to have D, non-zero, because if the D non-zero locations were in the location not corresponding to PD minus 1, certainly it still has 1. If it was non-zero in if one of the non-zero states was in PD minus 1, at least one of the states has to be non-zero, because
DX and dependent will have the same.
Will have the same. It need not have the same Hamming weight, no?
It is stored for this term.
No, it could be the case that it might require you to do something that my distance might have become actually better. It could have been that every non-zero code word actually put its weight on at least one of weight on at least one PD minus on the PD minus 1 coordinate, and then in which case that possibly when that gets spread, it spreads in multiple coordinates. It could happen.
If it's zero, that is fine. Like when you see that, you can have two non-zero things adding up to zero.
Yes, yeah. So So all I want to say is first proof distance, the distance proof. D, sorry, C prime, the distance of C prime is at least the distance of C, which is equal to D. So you get that distance. But I also want to claim it's actually R locally recoverable. Why? So suppose any message symbol, you drop off one message symbol. What are the locations that you are going? Suppose you drop off the ith message symbol. Where can you recover it from? Huh? Go so let I be anything in K. Huh? Let Sji be the Sji be such that I belongs to. So you define Ji is such that I belongs to Sji. Now certainly you know that from this set, which set do I want to say? K minus 1, sorry, not K minus 1. The set Sji and how do I write this? So that's right. I'm going to define what is Ri. Ri is going to be all the locations corresponding to Sji union this particular location corresponding to the Sji symbol, which is exactly what, which is it's K plus D minus 2 plus Ji. That's the location of the. All I'm claiming is Sji contains the support of all locations in Ji. In it. So this location that is since Q of Ji, the support of here I'm crucially using support of Q of Ji is exactly equal to Sji. That's the definition. Therefore, if you have all the locations of Sji, sorry, a minus. Minus 5. So you had all the locations in Sji minus I. And the support of Qi. This is so you have a linear combination of everything here except I, including I. Therefore, if you had all of them and this, you can certainly recover the I symbol. Not saying anything. I'm just using the fact that the support of the thing is the whole thing. So you for every K we get this. This K is a very simple construction. And notice this message length is extremely good. The usual what is the I want to ask what's the rate of this code? Rate of the code. So MDS codes we are going to have are going to take K to how much? K plus D minus 1. That's N. That's the blow up and the K is going to go this way. If you wanted distance D, you have to pay at least D minus 1 additional parity check bits, you have to add it. And here I'm saying, I'm doing if I want RD, MLRC, all I need to do is K going from N to K plus D plus K by R minus 1. Minus 2. So it's just a little bit more. So for every R, you're going to pay a little more. So this is a linear fraction in this one. So think of R as 10. I will willing to recover from 10 this ones. That's the amount you're extracting. So it's comparable to the singleton bound that way. You can get rates which are close to 1. Is this fine? It's a very simple construction. What we will now show actually is this is optimal. If there's an RDMLRC, you cannot do better than this. So a singleton-like bound. Let's see. Okay. LRC. Then n has to be greater than k plus d plus k by r minus 2. Okay. How am I going to prove this? So, suppose we constructed suppose we had two sets. Suppose we have two, suppose we partition, suppose we have two subsets of the coordinates, subsets of n, such that they have the following. So we have two subsets, let's call it S and T, which have the following property. One, yes, intersection T, S and T are disjoint. So these are disjoint for the things on this one. Two, size of T is strictly less than K. Three, T implies yes. What do I mean by this? So the same way I mean, if you know the code word locations on T, you can imply the code word locations on all of this. That's what I mean by that. The same thing where I meant Ri implies one. So if you know the code word locations on T, you get all of them, then you know the entire code locations on S. And I want to say that you must know something about this must put some constraints on the distance. So before showing something more, let's recall how did the proof of the Singleton norm go? So we projected it on we took a set of k-1 coordinates. We did show that two code words have to completely agree on. There must be at least two code words which fully agree on these k-1 coordinates. So the distance should all happen only outside. Therefore, the distance can never be larger than n minus k-1. This is what we did. Let's do the same thing over here. Now let's look at. So I want to claim now. Let's look at S union. Yes, yes union T. Notice because T is of size smaller than K. There will be two code words which fully agree on the locations in T. It can't be that every code word has distinct because there are only sigma to the k-1 possibilities for T. There will be two code words that fully agree on this one. But if they fully agree on T, they fully agree on S. Therefore, the distance can only be what happens in the complement. The distance can never be more than, which all of this should imply. All of this should imply the distance of the code, D of C, should be greater than or equal to, sorry, should be less than or equal to n minus size of T union S. This is what we have. So because of this, you will get the n, so we will get at the end of this, and you'll get n is greater than or equal to D plus T union S. That's one way of proving this one. So we will use the RD, this one, to basically get T union S to be of that size. T union S to be of size K plus K, the ceiling of K by R minus 2. If I can get it to be that, then I'm done. So the strategy is going to be very similar to Singleton. That's why I call it the Singleton-like bound. So we will construct T and S which have this property. Fair enough? Is this correctly clear? So let's now look at it. Okay, so I want to construct T and S. And what we want is P implies S. So the point is certainly what do we know of the T operator? We have Ri's imply I. We are going to use that to construct this. So let's construct T and S sort of in a greedy fashion. So let's construct T and S. Construct S and T as follows. Initialize ST to be empty. So S we will set it to be all subset of K. S will never go larger than K. T will be all over the place. T will be all over the place. But all that I want of S and T is only those 1, 2, 3. Then a single. This is basically a Singleton-like. This is a Singleton-like 2. So what should we do for this one? We want to do the following. While S is less than K minus 1, the floor of K minus 1 R, let T belongs to K be the first index in K outside S union. Firstly, I have to show that the way our algorithm I'm writing it is as if they will exist. One, we will prove that such a T will always exist. What I will do is I will add this guy to it. And then now because I added T to it, I need T to imply S. So I'll have to add all of RT into it, but I can't add all of RT because some parts of RT might be in S. So I will add only RT minus S. Okay. Is that going to cause problems? The point is we will maintain the variant that T always implies yes. T certainly implies yes to begin with. So even though I didn't add the S coordinate, those S coordinates are already inferred by what was the previous T. Therefore, I could by doing this, I will also so the point of this loop, this way I'm constructing this object. So basically, we are asking, is there a K that has not yet been T that has not yet been added? So I'll increase it to yes. Now when I increase it to yes, I want to expand T so that I can ensure that T implies yes. So what put T, I have to put an RT into it, but I can't put all of RT because I have to put RT minus yes. But the variant is still maintained because all the elements of S are already implied by T. Therefore, putting RT minus S is not an issue. So that's the entire, that's the loop. Output yes and T. So let's see what is the S and T that we get at the end of this. Firstly, I need to also show that as long as so at the end of this, you're going to get, I want to get if this loop continues at the end. Actually, before the end, let's see. I want to say, as long as S is less than K minus 1 by R, I want to say this, there will always be a T that satisfies this property. Why?
Is union P is at most R times the number of iterations.
Yes, union. Yeah, it's yes, but that's the R times in the whole set. How do I know that S union T is S union T is R times an R times the number of iterations, but that's in the that could be S union T could be larger. I want to say there's an element in K that is not there. Your thing will tell me there's an element in M that is not there in S union T. But I want to actually say there's an element in K that is not there. So for that, we notice that look at any RT. For any Ri, you do your same argument for any Ri. What is Ri intersection K minus 1? Intersection K, how large can it be? Huh?
At most one.
Can it be Ri?
The RI is the set of coordinates you query.
From which I can infer I. The other messages don't imply anything on this message. This is one. So Ri intersection K. Ri should necessarily have something outside K. So it can't have, Ri cannot be fully in K. So Ri is at most, this is at most R minus 1 is all I want to say. So you know, Ri is of size R. It can't be the case that Ri intersection K, Ri is fully contained in K because the K message, these K because Ri certainly does not include I. And certainly the other message symbols don't tell you anything about I message. So it must include something outside, and our construction did have this feature. And now we'll do whatever you said. Therefore, now let's look at exactly what Sridhar's argument said. Let's look at when you're adding SNP within K, how are you growing? Within K, each time you are adding an element of your yes is incrementing by size 1 each time, and Pi intersection K is increasing by size at most R minus 1. Therefore, if S is less than K minus 1 R, then and K minus 1 R, there's always some guy still in K which has not yet been touched by them. So while all I'm saying is why size of S is less than K minus 1 or yes union T intersection K. What can this be? This is at most R times size of S, and this is strictly less than K minus 1. They will always be. They will
K
always.
minus 1 by R.
Huh?
It is modest less than from K minus 1.
K minus 1 by R. Yeah. K minus 1 by R. Therefore, this is R times S. Therefore, that will be strictly less than K minus. Strictly less than or equal to K minus 1. Therefore, you do have one more element. So as long as this is there, you will keep on. As long as S is not K minus 1, so the end of the loop. We have size of S is exactly K minus 1 by. You got okay? And I also want to say size of this and size of T because of this is less than or equal to K minus 1. T is at most, T can have at most R times, each time you're adding only R times the size of 1, therefore T is so this T is most R times size of S, which is certainly less than or equal to K minus 1. So you have ended up with this. And at the end of loop, you have this, you have 1, you have 2, you have 3. What do you have? I have T. C implies yes. This is an variant that we can take. I want to try to make T even more larger. So let us see. Let's look at how do I do T even more larger. So I want to actually push T all the way to size K minus 1. So I want to so we constructed this. So let's look at how the word looks like at this point of time. So these are the first case symbols. And S is some chunk here. T is something here. T is something here. I want to say, and we know that T implies yes. I want to say they do. I can expand. So what can I say? What can I say?
Why combination to be why mod of achieving T is less than K minus 1.
No, I want T to be less than K minus. I want to go T all the way to K minus 1.
You just.
No, I can, now a point is I can add more. Question is, are there more symbols out there? If there are more symbols outside, I can keep adding them to.
Yes, sir. Data translation condition be why HNUT is not the whole of it.
No, but if I cannot guarantee that there will be a T in yes. So the point is, you will do this first, do this in increment yes and T, and then after a while, I won't increment yes anymore, I'll just keep incrementing T. So that's what I'm going to do now. Now I'm going to say, can I add? Are there more elements? Have S and T together exhausted the whole space? Can they have exhausted the whole space? Because notice that whatever is written in T already implies yes. Therefore, the number of code words is if S union T is everything, they can be only sigma to the k minus 1 code words. They cannot be more than sigma to the k minus 1 code words. But I know there are sigma k code words. So therefore, there are locations outside this, outside S union T, certainly. Add them. This condition will still be maintained. You can keep adding them till T is equal to k minus 1. So nothing is going to get violated. So all I'm going to do is expand, just use this argument. So, add more elements. So add k minus 1 minus mod T elements from n minus S union T to T such that 2 gets replaced by 2 is replaced by mod T equals k minus 1. And I say you can keep doing this, nothing changed. You can, as long as T is not equal to k, you can keep on adding this. Actually, you can add it all the way to T equals k also, but I'm going to stop at k minus 1 because I need it for the singleton bound. I want T to be slightly smaller than. Now I want to claim this P and S have this property, that is S intersection T is empty. T is less than k, T is all the way up to k minus 1, and TC implies S. Therefore, you are going to get that TC is less than this. In particular, you are going to get that by singleton bound like argument. You're going to get that n is greater than or equal to, what was that? What was that we had? N is greater than or equal to B plus T union yes. What was that? B plus k minus 1 plus k minus 1. What? This doesn't look like what we had, but we just observe that this is D plus K plus you just observe this. Let us K minus 1 by R is the same as K by R minus. The ceiling of K minus 1 by R is exactly the floor of K by R minus 1. Check that this is true. So this exactly gives you what. I'm going to take that more. So what did we do? We constructed a RT-MLRC, which, so we first put the second we put a singleton bound like thing for RT-MLRCs, and then we also showed a modification of the installment code which achieves this one. Now you could ask a little more. Do we want just an RT-MLRC? Why can't we get an RDL? Because thing goes down. If a data server goes down, you want to be able to recover it and patch it up and continue the process. That is, here right now I'm saying if a some data server corresponding message goes down, I'm able to recover it. If the data server goes down, you want to be able to recover it and put it back in and continue the process. So you want to actually have an RD LRC, not just an RD MLRC. So what we'll show, what I want to ask is, what about RD LRCs? Or do you have better bounds? So notice that this bound also implies for RD LRCs. So can we construct RD LRCs which match this bound, or there you have an even better singleton bound? What we will now show is actually you can construct an RD LRC also that matches the singleton. So next is going to be a construction of RD LRC. Matching the singleton. And the nice thing about this is going to be, it's as in the previous case in the construction of the RD MLRC, it's going to take the resolvent code and sort of massage it to get it. Actually, the massaging is actually going to be even nicer than what we did previously. Previously, it was not a rate solvent. The code words were not rate solvent code words. What we now do is actually it will be a subcode of the rate solvent. We will take a particular rate solvent code and it will be a subcode of the rate solvent code. We'll select certain, it will be a subspace. The rate solvent code is a subspace. We'll choose a smaller subspace of it. So just because it's smaller subspace, it will inherit the distance from the rate solvent. The distance will just come for free this way, but the smaller subspace will be to make sure that the original rate solvent did not have locality. We will sort of take the smaller subspace to force locality into the rate solvent code, and we'll get locality for all the code word locations. So I'll spend 10 minutes and finish this one. So basically, the theorem which we will do is the following. So let n greater than k greater than equal to r. So I want to get locality r, which is strictly smaller than k. Smaller than k, but we want get the locality and q be a prime power. So I'm going to get this column. We will make some niceness assumptions. We'll assume that r plus 1 divides both n and q minus 1. We'll assume this. I think you can get around it, but our construction will be cleaner this way. So then we will show, then we'll show, then we will and we give an explicit construction of a NK Q code with the NK Q code, which is RD LRC with T being exactly whatever T is specified by the D will be equal to n minus k minus this. Okay. Actually, that's more even simpler. I'm going to just assume n is equal to q minus. So I'm going to evaluate on all locations of the. So we're going to, with the read solvent code, when we take this prime power, we're going to evaluate on all locations of all the FQ star location. That's going to be the code I'm going to take. But I'll tell you what k I'm going to choose. But now because r plus 1 divides q minus 1, there exists an element omega in FQ star whose order is R plus 1. Whose order is R plus 1. That is 1 omega square omega to the power R for all distinct elements, and omega to the power R plus 1 comes back to. And we could very nicely use this property. So it's basically you're going to use some algebra. It seems like a very combinatorial feature you want. We'll use Reed-Solomon code and with the sum or algebra to get this an RDL LRC, which is LRC for every coordinate location, not just the message. Okay. So let's just set we have D and K. Let's just construct. So I given this. So let K prime be the smallest integer such that it's a funny definition, but we'll see. I'll give a more direct definition shortly. But this is a funny prop. This is the property of K prime I will use. So K prime is the smallest integer such that when I multiply K prime by R and R plus 1, and I take the floor, I get K. And I take the ceiling, I get K. I want to confuse left, right, I confuse floor and ceiling. So I want this to be K. Notice among all, so you'll take the smallest of this one. An equivalent way of defining this. Okay, this is the property of K and K prime I will need, but an equivalent way of defining. So notice that if K prime has this feature, what should K prime? K prime should be equal to, sorry, rather K, if the above is true, K should be equal to K prime R plus some A by R plus 1. This should exactly be K. For what A? What is the bounds on A that you can give? A should be certainly less than or equal to R because of it. Can it be 0?
R plus 1
Huh?
if R plus 1 divides K prime is
Well, no. Why? No. So just this, because of this condition, K should be K prime R plus some A. That A is just to make this quantity a multiple of R plus 1.
if R plus 1 divides K prime.
Yeah, it's going to be an issue. It's going, if R plus 1 divides K plus 1, R plus 1. So then it won't be the small. The K prime is the smallest integer. Then they will be the guy smaller than it will also have worked. Just one less than it would have worked. The K prime won't be. So I want to ask, can A? So A is right now A is some number which is 0 and R. My question is, can A be 0? I have claimed A can't be 0 because if A is 0, K prime, which is one smaller, will also have satisfied this property. So all I want to say is this is true. This is we have this feature. And this is what this is exactly equal to. So now I can rewrite, because of this, I can rewrite K prime as R plus 1K minus A by R. This I'll write it as K plus K minus A by R. But because A is non-zero, this is nothing but K plus the ceiling of K by R minus 1. Right? Okay, so that's the definition of K prime I want to use, but I want to say that if I chose K prime that way, it actually has that property. That's the property I will use. But K prime, to make a straightforward definition, this is the K prime and define that K prime has that property. This is all juggling with rows and ceilings. Okay. Now let's just construct the code to be n k prime Reed-Solomon code. The Reed-Solomon code which takes k prime method symbols, blows it up to k, blows it up to n. And by definition, it has the required distance that I wanted to have, because the distance of a Reed-Solomon code, the distance of this code is what? It's n minus k prime plus 1 minus 1. So what is that? That is n minus k minus k by r. Plus 2. Yeah. So that's the distance of this code has this feature. What I want to show is that so the code, final code, so this will be C prime. The final code which let's call it C. The final code which we construct will not be C, but will be a subcode of C. Therefore, it will inherit the distance from C, but it will inherit, but we want to ensure that it has R local records. So notice that C has distance D. C has distance D, but is not R locally recordable. It's an MDS code. We've done in 5 minutes. So let's look at so now let's look at U, which was 1 omega. This was omega to the power of R. I want to claim that suppose you multiply it, you look at this polynomial x minus u, u in u. What is this polynomial? What happens when I expand this out? What will I get?
1 plus u a x plus x plus
So certainly it's an r plus 1 degree polynomial. I want to claim actually it's this polynomial. Firstly, notice that every u is a root of this. It has to be this polynomial. These are all distinct pairs. And this has to be this. I have chosen it to be that. So x bar r plus 1 minus 1 is the object. So now, once you have this, so let's forward. So let's look at the location u alone. Let's now do a recovery process only for the locations in u. We'll look at the locations outside u later on. For every location in u, I will tell you that I can sort of get a linear. I can recover. I have an R local recovery process. That is what we will do right now. So we have these n locations. U is one. U is actually a subgroup of it. U is a subgroup of the multiplicative. So there are n locations, which is this is FQ star. It's of size n. U is of size r plus 1. It's a subgroup of FQ star. In fact, what we will show will be true for the following. So now you can look at multiple cosets of co-subgroups. What do you call them? The corresponding. What do you? The cosets of U. The cosets of U in this. So there will be some alpha U, alpha 1 U, alpha 2 U. The entire space is divided into this. So the way our final algorithm will go is have the following feature. That is, suppose you have this particular location is you want to recover. You will show that you will look at the other elements in that particular coset. From them, you will be able to recover this location. Notice. So I haven't really told you how I'm going to restrict the Reed-Solomon codeword. So I'm going to restrict the Reed-Solomon codeword. Take a subspace of the Reed-Solomon codeword. Such that on every such coset, any element here can be recovered as a linear from the other elements. So in particular, what should that have a feature? There must be a linear constraint involving all the elements in this. So there must be one linear constraint which involves these R elements. There must be another linear constraint which involves all the there are R plus 1 elements here. If there is a linear constraint involving all the R plus 1 here, if those R plus 1 satisfy linear constraint, notice that Reed-Solomon code does not satisfy this property. Then 1 second. Is there a block? Maybe function. It's at 11:30.
But there's some snacks at the.
Yeah, it's a rocket or not. So what do you want? If there is a linear constraint in which the support of the linear constraint is all the R plus 1 guys here, then it's R locally recoverable. Any guy drops, I'll use that linear constraint and the other R guys to recover. So what we want to show is we want to construct a Reed-Solomon subcode of Reed-Solomon codeword so that if there is a linear constraint involving these things. Notice that the Reed-Solomon codeword does not have any such. The Reed-Solomon codeword the linear constraint because any K location, any K prime location are completely free. K prime is much larger than R. But I want this property. So what do you want? So let's look at. So let's just look at the. Let's say I will do it only for you. The proofs for the other courses will be similar. Yeah.
Since
So
for doing that,
mhm.
we can transfer any other person, we can transfer it inversing our element in our file.
But why will I know the value here? Why will I know the value here? If I know what
constants and
this one's the alpha goes into the evaluation of the polynomial. I don't know how to. So if I know it here, I don't know how to do it over here. But the same proof will hold good. So let's look at the Reed-Solomon code restricted to U. What's the Reed-Solomon code restricted to U? So I'm having some polynomial P of X. The P of X restricted to U. Now, when you care about restriction to U, you really don't care the whole Reed-Solomon codeword. All that you care is you care about PU of X, which is exactly P of X mod X power R plus 1 minus 1, because you can model, you can do this constraint. The value evaluation of the polynomial is not going to change. Therefore, all that I need is PU of X. Now, let's look at the degree of PU of X. The degree of PU of X will be at most R because of this. If it was strictly smaller than R, then if it is at most R, then you need all the R plus 1 terms here to know what PU of X is. But suppose you knew that PU of X is always when the Reed-Solomon code, which the subcode of the Reed-Solomon you choose, have the property that PU of X will always, for every P in the Reed-Solomon in the code which you have, has degree less than R. That means there will be any polynomial of degree less than R on R plus 1 point, they will involve a linear constraint containing all of them. It's only the full degree which is going to have, because you will be able to interpolate and get the other case. So that's all I'm going to claim. I want to claim if you're going to force the Reed-Solomon codeword to ensure that when I do this restriction, PU of X drops to less than R. And what happens? What is this restriction? This restriction is going to take just X power R plus 1 and replace it with 1. Therefore, the code is just obviously the code is just. So it's just C star is exactly C star is set of all evaluations of P alpha and Q star. So degree of P is less than K prime, whichever we have chosen. And furthermore, I want these properties that if I write P of X as summation Pi X power I less than K prime, I want Pi to be 0, Pi to be 0 whenever I is congruent to R mod R plus 2. So these will be the ones that contribute. So whenever I is R, that's when it contributes to the R power. So notice, all those will set it to be 0. All those will set it to be 0. So now when you do the reduction, you ensure that PU of X will always be this one. So this will be the subcode of Reed-Solomon code that we will pick up. So this will be the subcode of Reed-Solomon code. So C star is our final code, and then you can check. You can do a dimension counting. That is, I have dropped the dimension has dropped from K prime a little bit, but how much it has dropped will be exactly So you can figure that out. How many guys are zeroing it? So many guys are dropping the dimension. This will be the code. We are almost done. So now there's a linear constraint among the elements in U. But we need one more property. I need the linear constraint to involve all the elements. Because if it doesn't involve all the elements, then one of the elements will not be, you will not be able to decode one of the elements. You want, just like we wanted the support to be full, you want the support to be all of U. But that is true because there will be at least one polynomial which will have, there will be one, when you do this, there will be at least one P which has, take the P which has just degree R minus 1, the degree R. When you reduce it this way, take the P which has full degree R. This polynomial, a degree R polynomial, the linear constraint, you have to involve all the R plus 1 guys. You can't involve anything else. Yeah, take that guy. That guy has to involve all of them. So in particular, you will have that linear constraint should involve all of them. That's the end. That's the whole. So this is actually, it's this code which is used in, was used, I do not know if it's still used, but Microsoft Azure, actually they use this. It's a very, the rate of the code is extremely close to being, very close to the recoverable code, but yet it has a recovery process. So they were able to replace the repetition code. Okay, I will stop. We have a next property.